Good morning and welcome to this lecture in our course on mechanical operations. In the last lecture we started talking about size measurement. Again, size along with shape is the most distinct characteristic of a particle that affects its behavior in many of the mechanical operations that we will be talking about later in the course. So when we talk about size, I mentioned that there are essentially two methods of size analysis, the static method and the dynamic method. And we talked a little bit about various dynamic methods that rely upon setting the particle in motion and measuring its dynamic characteristics and also matching the dynamics to the application at hand and obtaining a very functionally relevant diameter of the particle, but not a single particle. Typically, again, the dynamic methods obtain the average or mean size of a population of particles rather than single particles. But suppose you did want to measure the size of a single particle, then how would you do it? That is where the static methods come into play. Now, there are two parts to it. When you are doing static size measurement, first you have to capture the particle. You have to somehow bring it to rest on some surface or suspended in some medium where you can examine it, right. That is the first step, and the second step is the analysis part. So, let us first talk about the collection part. There are many methods for collecting a particle for inspection. The most common one that I am sure you are all familiar with is filtration. Whether you are analyzing particles that are suspended in gas like air or suspended in liquids like water, a convenient way for doing that is to filter the particles onto a medium and then analyze the filter. There are two types of filters. There are the fibrous filters and there are the membrane filters. Fibrous filters are actually extremely effective in separating particles from the medium. A fibrous filter presents extensive surface area, so the likelihood that a particle will get trapped is extremely high. So, the best fibrous filters can virtually guarantee you 100% filtration efficiency down to submicron sizes. However, you cannot use fibrous filters for inspection purposes because once the particles get trapped in the fibers, you cannot see them anymore. And the whole point of static measurement is to be able to inspect the particles after you have filtered them. So, using a fibrous filter, even though it is extremely effective, defeats the purpose. So, we rely on instead membrane filters. A membrane filter has a flat surface with small holes punched in it, and particles get trapped on top of this filter surface. So, they are available and exposed for further inspection. There are different types of membrane filters. There are polymeric filters which are very effective for analysis of metal particles because of the contrast, and similarly there are metal filters which are effective for inspection of polymeric particles, again because of the material contrast. And so, both types of filters are widely employed. There are filters that are specially designed for microscopic inspection. There are filters known as sticky stubs which can be directly mounted into a scanning electron microscope without having to coat it with some material. So, that technology has evolved really well. Now, other methods that are commonly used for collection of particles, there are different methods based on the size range of the particles you are looking at. If you are primarily trying to capture large particles that have significant inertia, then methods based on inertial impaction work very well. There are devices known as batch settling apparatus. In a batch settling apparatus, the particles, as the name suggests, are taken as a batch sample and the particles are allowed to settle. And as they do, there are collector plates that are installed at the bottom of the collection chamber, which simply collect the particles through a sedimentation or settling mechanism. So, fairly easy to visualize, but the drawback of this method is it is only really effective for particles that are large enough to have significant inertial velocities. If you have fine particles, they may never reach the bottom and get filtered or captured, they may just keep floating around in the top of the tank, right. Another method which is kind of an extension of this is, instead of allowing the particles to settle vertically, you actually entrain the particles in airflow and blow it past a series of collector plates that are mounted vertical to the flow direction. And in this type of a configuration, the actual setup that we use will have tubes of different diameters. So, you will start with a large tube, and then the next piece will be a little smaller in diameter, and the next piece will be even smaller in diameter, and so on. The idea here is that when this airflow is introduced with the entrained particles, as the diameter keeps narrowing, the velocity of the airstream will keep increasing, right. So, what will happen is the largest particles will get captured in the first stage. The finer, smaller particles will then get to the second stage and then be captured, because it is a Stokes number effect. So, as the particle size drops, you make it up by imparting an additional velocity. So, by using this kind of a continuously narrowing tube diameter configuration, you can ensure that particles across a variety of size ranges are captured with equal efficiency. So, this is known as a cascade impactor. A similar arrangement is what we call an impingement collector. Impingement is a particle collection mechanism that comes into play just below the range where inertial impaction is important. So, again, for large particles, inertial impaction is the dominant force, and that is used in the batch settling chamber and the cascade impactor. For particles that are just below this, and size wise, let us say we are talking about up to 50 microns would be considered the inertial range, where there is a significant inertial impaction flux. The size range between about 10 microns to 50 microns would be called the impingement range, where the particles are not so large that they will be inertially scavenged effectively, but at the same time they are large enough that they will be able to deviate from the streamlines of fluid flow. I mean, the whole definition of inertia is that the particle must be able to separate itself from the flows, from the streamlines of the flow in which they are entrained. Any particle that has a significant deviation is considered to have significant impaction velocity. In impingement, the differentiation between impingement and impaction is fairly subtle. It is probably worth sketching it. So, if you have a surface and on which you are trying to collect a particle, this could be a cascader plate, it could be a filter. If you are trying to capture particles by inertial impaction, you typically want the particles to come down in this direction, that is perpendicular to the plane of the collector. And as they do, the streamlines will obviously go like this, right. It is a stagnation flow. However, large particles at this point will deviate from the streamline and head straight towards the surface of the collector. So, that is basically how an inertial impaction collector works. In the case of an impingement, so this is an impaction mechanism. In the case of impingement, again let us say that this is a collector, the flow direction is parallel to the collector. Impingement is the mechanism by which the particles that are in contact with the plate get collected on the plate. So, it requires that the particle must follow a streamline which brings it within a diameter of the surface on which you are trying to collect the particle. So, that is the primary differentiator between impingement and impaction. Here the particles do have sufficient inertia that they will separate from the flow, but they will only do it close to the surface on which you are trying to collect, right. So, these particles, again if these particles are of this size, these particles are of this size, they are just not large enough to be effectively captured by inertia, but they are large enough to be collected by impingement forces. So, in an impingement collector you will set up a set of collector plates in such a way that the particles are entrained in flow and then passed by the collectors in a horizontal flow or parallel flow configuration and many particles will collect by impingement. Another type of classifier which works well for even smaller sizes is called a winnowing classifier. So, in a winnowing classifier you have particles and they are entrained by a high velocity airflow that typically comes from the bottom of the chamber. Here you are relying on more the aerodynamics of the particles. So, you are looking at particles whose size range is below the impaction regime and below the impingement regime as well. These particles are quite likely to follow the streamlines that they are entrained in. However, they are still in a size range where there is some inertia. So, different sized particles will follow the streamline to different extents. The lightest particles will basically behave almost like vapor molecules. So, the smallest particles will get blown to the outer diameters, whereas the largest particles that have more inertia will stay in the center of the chamber. So, they are more likely to, if you have a collector here, they are more likely to be collected in this region, whereas the finest particles will collect on the walls. So, the winnowing process, I am sure you know people use it even in homes. Winnowing refers to separating particles by size and mass based on their ability to follow a turbulent airflow that you create. Okay. So, what are the other methods that we can think of? There is a method that is known as a Phoretic classifier. So, in a Phoretic classifier, again you have an air stream or liquid stream in which you have particles that you are trying to collect for inspection. Let us say that these are charged particles, okay, and let us say that they have a distribution of charges, and let us say that the charge depends on size, and by the way it does, in any naturally occurring particulate population, the amount of charge that a particle carries does depend on its size. You can say that as particle size increases, the charge on it increases also. So, suppose you apply an electric field and you set up a charge differential, then what is going to happen? The first thing is the particles are going to separate based on the charge that they have, opposites attracting and so on. And you can certainly use this technique to simply collect the particles. So, all the positively charged particles will head to one plate or one surface in this tube, and the negatively charged particles will head to the other side. So, you are essentially using electrophoresis as a mechanism for collecting particles. Another way you can do this is using temperature differential. It turns out that particles that have most particles are affected by a temperature gradient in terms of mass flow also. So, a temperature gradient does not only affect heat distribution, but also mass distribution. There is something called thermophoretic velocity which all particles have, and the finer the particle, the greater is the thermophoretic velocity, and particles will typically move from high temperature to low temperature when you expose them to a temperature field. So, here again if you have a T high here and a T low, particles that are heavier than the gas that they are entrained in will go towards the low temperature plate, whereas particles that are lighter than the gas will head towards the hot plate. So, you get in a sense not only collection but also classification. You are kind of simultaneously separating the larger particles from the smaller particles, or let us say the heavier particles from the lighter particles as part of your collection process. So, it is a fairly powerful technique, and there are many types of Phoretic forces. For example, if you have magnetic particles, you can use a magnetic field as a collector, right. So, what you do in this case is you enhance the natural mobility of the particles by means of an applied force field that these particles respond to because of certain properties that they have. Another type of classifier is called the isokinetic classifier. The thinking here is that, let us say that you have a lot of particles in an area. For example, let us look at this room. Suppose you want to sample the particles in this room for analysis. How would you do it? Based on what we have discussed, you can think of various things. You can just set up collector plates, right, and then they will collect particles by inertial impaction, or you can take some air from the room, suck it through a filtration apparatus, collect the particles on a filter, and so on. But the problem with that is that when you collect particles at one location in this room, how do you know it is representative of the particle distribution within the entire room? You do not really know that. In fact, there may be certain areas in this room where the airflow is significantly different from the airflow in the other areas. For example, near the corners, you may have stagnation regions where the flow is just not present. So, the air continuously recirculates in that area. Suppose you did your particle collection in that area, would that be representative of the room? No, clearly not, because it is very different from most of the environment. So, isokinetic sampling basically refers to sampling particles from an environment at the most natural location. So, the first thing you would do is characterize the airflow in this room, right, and then you will set up your collection equipment in such a way that it aligns to the airflow at that specific location. So, if the airflow in a particular area is in this direction, then your collection device must also, either if you are trying to capture large particles, it must be perpendicular to that direction, or if you are trying to collect by impingement mechanisms, it should be parallel to that airflow, or if you are trying to set up a filtration apparatus. Again, filtration pretty much depends on a normal entry, perpendicular entry of the airflow onto the filter surface. So, isokinetic sampling simply refers to really understanding the airflow configuration at a particular location and making sure that your setup is optimized for collecting particles at that location. So, in a room like this, you may need to set up multiple samplers and all at different orientations, configurations and so on to get a really good description of what is happening. The reason for that is this room, even though it is a clean room, it is not a clean room. Clean room is two separate words, clean room is one word. There is a big difference between the two. A clean room is one that has been maintained clean, but it is not designed to operate at a predetermined cleanliness level. A clean room, where you write it as one word, is a controlled facility where you manage the whole facility in such a way that the particle count per unit volume of air inside the room meets a certain specification. So, when you think about it, suppose you want this room to meet a specification of, let us say, no more than 100 particles larger than half a micron per cubic foot. How would you do it? The first thing you need to do is control airflow in and airflow out. You have to make sure that any air that comes into this room is directed through filters which will remove particles and other contaminants from the air and allow the air then to enter the room. And similarly, you have to make sure that you provide a return path. The air that is coming in must have a well defined path for how it exits the clean room, right. So, that is how a clean room is designed generally. The air comes in through the ceiling and it typically exits through the floor. The floor will typically have little holes in it through which the air will exit the room, and then you can even recycle the air when you are doing it that way. So, in that configuration what happens? The airflow is very controlled, right, it is vertical, it goes from the top of the ceiling to the basement, and you can sample the airflow at any location using this isokinetic sampler. You will find that at virtually any location the airflow is always in one direction. except right near the floor. So, and near the walls, for example. So, you kind of, if you are trying to do manufacturing in this type of a clean room, you will make sure that you do the manufacturing only in areas where you know that the airflow is controlled and operating as per your requirements. So, in a clean room, you kind of know how the airflow is happening, and therefore, you can choose to do your sampling pretty much anywhere in the clean room, and you will be fairly representative of the entire room. And you can also use filtration as a mechanism to control how clean the room is. So, the other type of sampling that we can do is particularly suited to very, very fine particles, and these are known as diffusion batteries. In a diffusion battery, you take advantage of the fact that very fine particles, that is submicron to nanometer range, primarily are transported through diffusional processes. Diffusive velocities dominate over all other induced velocities of the particle. And so, you set up what are known as diffusion screens. You let the particles, again you have an entrained airstream in which you have particles, and you set up these screens at different locations along the flow path. So, here what will happen is the finest particles actually move the fastest. Turns out that diffusivity scales as 1 over particle size squared. So, the finest particles will be collected in the first screen itself, whereas larger particles will take longer to diffuse from the bulk of the flow and find the collection surface. So, by using this kind of an arrangement, you can once again simultaneously collect and classify. Again, the difference is collection is simply collecting all the particles that are suspended in the fluid. Classification is separating them by size as well. So, clearly if you are going to be doing subsequent analysis to determine the size distribution, it is very convenient if you can, as a part of your collection process, you can also separate them by size, at least approximately, because when you talk about static methods of analysis, there are different methods that can be used depending on the size range of the population you are looking at. Again, if you have very large particles to look at, naked eye inspection is perfectly fine, but as the particles get smaller, you have to use magnification. The resolution of the human eye is about 200 microns. It does not mean that we cannot see anything that is smaller than 200 microns. I mean, we can we can see threads, very fine threads. The human hair is less than 200 microns, and we can see all that, right. In fact, the human eye can even see nanometer sized particles, but the resolution is something different. The smallest particle that you can observe is called the sensitivity limit. It just says this is the smallest particle you can observe. Resolution is something different. Resolution refers to the fact that even though your eye can see something, can it resolve this from another particle that is adjacent to it, and the human eye cannot. The limit of resolution for the human eye is only 200 microns. In other words, the human eye cannot tell apart two particles that are closer than 200 microns. So, that automatically limits your ability to ascribe size based on just naked eye inspection, because the problem is if you see something, you do not know that whether it is a single particle or whether it is two particles that are agglomerated or multiple particles that are aggregated, right. So, as soon as your sample contains particles that are smaller than 200 microns, you have to start using magnification. Magnifying lens, optical magnification is the simplest alternative, and it used to be that with an optical magnifier you could only go up to about 100x magnification. Now there are even optical microscopes that can go up to 10,000x magnification. The limitation again is, in an optical microscope the resolution is better than the human eye, but it is still only of the order of about 5 to 10 microns. So, you really do not want to rely On an optical microscope, if you are trying to size particles that are smaller than 5 microns roughly. So, what is the next thing you do? Electron microscopes, right. An electron microscope works by a totally different principle. You are actually collecting the particles onto a filter, and then you are impacting the sample with electrons, which causes emission of secondary electrons. These secondary electrons are collected and analyzed to do characterization of the size of the particle, the shape of the particle, and even the composition of the particle. You know, if you can combine an electron microscope with energy dispersive X-ray EDS or EDX analysis, you can actually even get the elemental composition of the particle. So, you go from naked eye inspection to optical microscopes to electron microscopes, and of course, there are many variations of this. You know, SEM has a resolution of a few tens of nanometers. If you want to get even better, you go to a TEM, tunneling electron microscope, which can give you a few nanometers resolution. There are also AFMs, atomic force microscopes, which can again give you nano dimensional detail in 3 dimensions because of the way that an atomic force microscope works. You know, as a chemical engineer, if you want to know not only the elemental composition of a particle, but the actual species information, you know, if you see sodium and chlorine in a particle, what is it? Is it sodium chloride, or is it sodium chlorate, or is it sodium hypochlorate? You do not know that, right? You are only seeing sodium and chlorine elements. But there is a technique called ESCA, which enables you to then go in and actually determine exactly what compound it is. So, all those methods become possible, but the downside is that if you are just trying to determine size, all these methods are an overkill, because once all these methods from electron microscopy to AFM, they are not intended as quantitative size measurement tools, they are intended as qualitative characterization tools. That is really where their power is. You know, it is something you do in a lab to really look at something in a lot of detail and understand everything about it. They are analytical tools. Size measurement, on the other hand, is a simple quantitative measurement, right. All you need is a number. What is the size? So, to use all these more sophisticated instruments for that purpose, it is kind of a waste of time, energy, resources. But if the particle goes below a certain size, you cannot use optical microscopy. So, what choice do you have, right? Actually, there is a choice. The technique that has emerged as the most popular for characterizing size when the particle is smaller than 20 microns, you know, actually up to 20 microns, as I mentioned yesterday, there are sieves that can do it, micro sieves. It is only when you start dropping below 20 microns, start heading towards 1 micron and sub-micron and nano sizes that you use that you need better techniques. And since the microscope based techniques are very laborious, expensive, and they require a lot of expertise, you need trained technicians to do an SEM analysis on a sample. So, people thought about it and they came up with techniques that are based on light scattering. Light scattering is now the most commonly used method for characterizing the sizes of individual particles as well as population of particles. And the reason for that is it is a simple technique. It is a push button technique. The operator does not need to know a lot of science or technology to be able to use it. Anybody can use the instrument. Of course, the design of the instrument, the calibration, all of that has to be done by specialists, but once the equipment is provided to a lab, it can be used very simply. So, how does it work? We all know that particles, suspended particles scatter light. You know, what is a good physical manifestation of that? Fog, mist. Why is it that visibility drops under foggy conditions or misty conditions? What is fog? Or it's basically very fine particles and droplets that are suspended in air, right? And they play havoc with light transmission, which is why you cannot see anything under foggy conditions, because the light keeps getting, bounced around in various directions. So, you lose your ability to see objects. So, given that, can we use that as a way for measuring particle sizes in that mixture that is suspended in air? It turns out that you can. There is a technique called turbidimetry, or turbidimetry is a technique that is widely used to characterize particle concentrations and by extension particle sizes in liquids. In fact, most metro water departments will use turbidimeters as a primary control over the cleanliness of the water that they have, because it is a very sensitive measurement of suspended particle concentration in the liquid. So, the way that turbidimetry works, if you have a beaker with some liquid in it and you have suspended particles and you shine light, obviously if there were no particles, all the light will be transmitted right through, right. But because of the presence of the particles, what happens? There is a transmission loss. Some of the light is reflected back, some of the light is scattered, some of the light is absorbed, and some of the light is transmitted. So, if you can look at the transmitted light I and relate it to the incident light I0, the ratio will actually tell you something about the suspended particles in the fluid, and in fact the expression is I equals I0 times exponential of minus ABCD. Anyone familiar with this law? Have you heard about it? It is called the Beer-Lambert Law or Lambert-Beer Law. A stands for the attenuation coefficient associated with the particle, B stands for this distance, the distance of transmission of the light through the sample, C stands for the concentration, and D stands for the D stands for the total exposed area or scattering area of particles in the sample. Okay. So, if you know this and you measure this and you know A, B, then you can measure the multiplication of C and D. Let us say that you know the concentration of particles, and you can estimate the parameter D, which is actually the total integrated scattering area of particles in suspension. So, this technique is not going to give you single particle sizes. However, what it gives you is exactly what I just said. It gives you the total light scattering cross section of particles suspended in the liquid. Now, that is a useful measure certainly, but does it yield size? Size is obviously involved. I mean, if you can measure the scattering cross section, you can assume that that is related to the surface area. So, the total surface area of the particle is 4 pi dp squared. From that, or pi dp squared, from that you can measure, you can extract a mean size, and this will be, we talked about equivalent diameters in the last class. So, this will be a scattering equivalent diameter. So, you can at least get a mean size of the particles that are in suspension. But supposing you want to get more detailed information, you want to know not only the mean size of particles, I want to know how many particles are in various size ranges. I want to know how many particles are in the 1 to 2 micron size range, 2 to 3, 3 to 5, 5 to 10. Can you do that with a turbidimeter? Actually, you cannot, because what it will tell you again is a total integrated effect. So, different samples may have different numbers of particles in the various size ranges, and they may still give you that same total scattering cross section. So, you cannot deconvolute the data and extract the two pieces of information separately, you can only extract them together. So, if you want to get information on single particle sizes, how do you do that? Actually, there is an extension of this technique also based on light scattering, which looks at how light is scattered. Suppose again you have a fluid with particles and you shine laser light on it and you look at the scattering of light from individual particles. So, if you have one spherical particle like this and you shine light on it, again it is going to get scattered, right. So, again you can talk about I 0 and in this case the scattered light intensity I. What would they be related, how would they be related? Clearly they will be related by many properties of the particle as well as the medium that it's suspended in, by the wavelength of the light, by the distance of separation from the light source to the particle. So, there are many parameters that will be involved and particle size will be obviously one of the most important parameters. If you look at the light scattered intensity I, it turns out that it is proportional to dp to the power 6. So, as particle size increases, the scattered light intensity increases to the power 6. Conversely, as particle size drops, there is a very significant drop in the scattering light intensity. So, so it is a very powerful technique because it is so sensitive to particle diameter, but it also presents a challenge because we are constantly trying to measure sizes in the submicron and nano ranges. If this happens, if light intensity is dropping so fast as particle size drops, how can you use this technique for the very fine particles? Actually, there is a way to do it, think about it. We'll discuss it a little bit more in the next class as well. So, in the next class we will talk some more about light scattering from individual particles, how does that enable us to measure the size of individual particles, and then we will talk about particle size distributions. Turns out that in nature very few particle populations are monodispersed, that is having the same size, they are all polydispersed. So, you need to be able to measure not only the size of a single particle, you need to measure the size distribution of particles that are in your sample. There are instruments called liquid particle counters and particle size analyzers that do this. So, we will talk quickly about those techniques in the next class. We will try to wind up our discussion of size analysis by the next class, and then we will start on the next topic next week. Any questions? Okay, see you tomorrow then.